Thanks everyone for being here. In today's presentation, we're going to go through the exploits that we used at PWN Berlin of this year. First of all, quick words about us. We are two security researchers from Palo Alto Networks, working mostly on the vulnerability research from the offensive and defensive sides. We also really enjoy participating to PWN events in general and speak at conferences. So thanks again to Hexacon for having us this year. We are very pleased to be here. Now, during this presentation, we're first going to go through some quick introduction about the context of the vulnerability that we're going to talk about. In the second part, we'll go through the 6-year-old bug that we find in the Firefox JS engine. Then we're going to show how we actually exploited it, and we'll finish the talk by a quick demo and a conclusion. So first of all, during that talk, we are going to go through a lot of JavaScript asynchronous programming. So back in the days, asynchronous programming in JavaScript was mostly done via callbacks, which led to a lot of issues. But the main one was the callback hell, which can be described as like a lot of nested, deeply nested code that was really hard to just read and maintain in general. And so in order to fix that, the JS specification came up with the promises, which is like a new abstraction, which is the new abstraction of JavaScript asynchronous programming in general, which fixes pretty much all the issues from the callback scenario. So eventually, it led to a lot more a code that was more readable, maintainable, and that allowed also a lot more composition in JavaScript asynchronous stuff. But that new abstraction, which makes coding in JavaScript easier, was actually relying on a lot more complexity inside the JS engine. So it kind of became a new attack surface for attacking browsers. And so if we take a look at some of the past vulnerabilities that happened in the past few years related to JS promises, we can see that they share some similarities. So first of all, they kind of define their like proper implementation of promises. And for that, they're going to use custom promise definition. They're also going to implement their proper custom resolve and custom reject implementation in the executor. And finally, redefine the static resolve method to implement also their proper stuff. And eventually, they will call a vulnerable API. So here, for example, we have custom promise.any and promise that's all settled functions that are vulnerable. So based on that, that leads us to talk about the 6-year-old bug that we find in Firefox. And our bug is out of bound right in the promise all settled implementation, which was present since like 2019. Which is the very first implementation, actually, of the API inside the SpiderMonkey JS engine. And so in this section, we'll first go through some of the internals that are required to understand properly what the bug will be about. And secondly, we'll go through how we discovered the bug, and finally, how to trigger it. So if you are not very familiar with the promise all settled method in JavaScript, it takes as an argument iterable of promises. So for example, here, promise 1, 2, and 3. And will return as an output an array of objects describing the outcome of each one of the promise. So if it's either fulfilled or rejected. Now, when you call the promise all settled API from JavaScript, inside the underlying JS engine, it will actually call a bunch of internal APIs. And we're going to go through some of them to properly understand what's going on inside the engine. Now, as a test case scenario, we are not going to use a default behavior like you can see on the left here, but we are actually going to use a custom promise, which is closer to the past vulnerabilities that we looked at, and that also closer to the vulnerability that eventually we found. So as a test case, we're going to use that JavaScript where we define a custom promise with some custom result function and custom reject function inside the executor, and eventually our proper implementation of the static resolve method. Finally, we're going to call the actual vulnerable API here, which the promise all settled, and with 3 parameters, like the 3 promises as a parameter. So when we call that promise all settled from JavaScript, we'll first call those 3 APIs in yellow here. And in those 3 APIs, what happens is we initialize 2 very important structures. The first one is values, which is eventually just a wrapper around values array, which is a JS array. And that JS array is actually the output of the API. So it will contain all the objects describing the outcome of each of the promises passed as an argument. Now, the second important structure that we initialize here is the data holder. And the data holder is just a JS object, which contains some interesting fields like a custom promise object, which is just an object constructed based on our custom promise constructor. The remaining count, which describe how many promises we will have left to process. The values array that I just talked about in the previous slide. And finally, a custom result function. And this function is actually corresponding to the implementation that we did in our JavaScript right there. So after those 2 structure initialization, we're going to call the command perform promise combinator function. So that internal API is it's a loop through the argument, the iterable argument of promises. So for each promise, we're going to first call the custom promise resolve, which reference to our static resolved implementation. So it will just execute that JavaScript function, and what it does is just returns a denable object, and that denable object has itself like just one property, den, which corresponds to a den function. When we go back to the internal API, we'll actually store that denable object inside the next promise variable and continue execution to the get resolved and reject function, where we're going to initialize other structures. And this function can be defined in 5 steps. First of all, we're going to push the undefined SpiderMonkey value inside the values array. Second and third steps are we're going to initialize the resolution function. Here we have actually a pair of functions, one resolve and one reject, depending on the outcome of the promise. And you can see here also that those JS functions are an extension actually of the default JS function, because they also store the data holder and the index related to the promise. Fourth step is we're going to increment the remaining count, saying that we'll have one more promise to resolve when it's time to actually resolve the promises. And finally, we're going to increase the index so we can go to the next promise. When this is done, we're going to actually store the resolution function pair inside those 2 variables and eventually call our den function with as a parameter those resolution function pair, which will call back to JavaScript and execute our den function with our 2 resolution function. So eventually, after the while loop is done inside that function, we're going to have for each one of the promise some resolution function pair. So for each one of them, each one of the promise will have one resolved and one reject, depending on the outcome of the promise. And they all store the data holder and the index related to the promise also inside their internal structure. So now let's execute the den function and see what happens. The first thing we're going to do is we're going to call the fulfill, which will correspond to our resolved element function here, and corresponds again to the internal API promise or settled element function. And this function is template function, which has for which you can pass it a kind. In our case, we're going to resolve, so the kind is resolved. So let's call that internal API. And so that API is actually the one that will perform the resolution of the promise. In order to do that, we're going to first, from the JS function itself, get the data holder, and secondly, the index related to the promise being resolved. Secondly, we're going to get the values array from the data holder and store it in the values variable. Then we're going to perform a check to see if the values array at index 0 here is undefined. And this check is to see if one of the resolution function has already been called or not, because promise can eventually be resolved once. So here it's undefined, so we can bypass that check. And now the next step is to create the actually output object, which is simple objects with two properties, status and value. And finally, we're going to set the output object inside the values array and decrease the remaining count, saying that we are done with that promise, so we can decrease the remaining count of the internal API. Now, if we call reject right after fulfill in our then function in JavaScript, it will call the same internal API, but this time with the kind reject. So we'll go through the same execution again, but this time when we arrive to the check of the undefined value at index 0, we can see that we already have the result object because the promise has already been resolved. So we're going to actually bail out from that function and return. Eventually, after all the promises are resolved, we're going to get 3 result objects, which will be stored inside the values array. If we go back to the last promise resolution, eventually the element store here will be full, and the remaining count will be decreased, so it will be 0. And that 0 remaining count will get us to a new code path that will execute the custom resolve function that is stored inside our data holder and pass it the values array as a parameter. And this will actually call back to JavaScript, where it will execute our custom result function that we define here, and the result argument here will point to our values array. So based on the test case that we just saw internally, we can see that custom promises allow us to control a few things. First of all, the static resolved implementation, and importantly, the then function, and when and where we call the fulfill and reject element function. Secondly, we can also customize the implementation of the custom resolve function here, and we can also have access to the result values array here and potentially perform some actions on it. So that leads us to talk about how we discovered the vulnerability that I will explain right after this section. So we have connected like similar implementation issues through inside the JS specification related to promises across different browsers, and found out some similarities. And so here we have 2 examples. The first one is related to the values array. When it is exposed to JavaScript via the custom resolve function, it was possible to trigger the garbage collector after the values array was trimmed. So the values array will move in memory, but the internal context inside the internal API would not be updated with the new pointer to that values array, so it will lead to memory corruption. The second example here is related to an issue inside the already called scenario in the JS specification, which will lead to, it will be possible to call the fulfill and reject, so it will decrease the remaining count by twice. So the values array will be returned to JavaScript prematurely, and so you could potentially change the values array, and so it will allows you to do a type confusion. So based on those 2 examples and on other examples that we studied, we found like some similarities, and went with a summary of all the implementation issues that we've seen. So the first one is the element resolution function implementation issues. So when and where those fulfill and reject functions are called. Second one is related to the remaining element count. So when and where the element count is actually incremented or decremented. And finally, how the user-defined JavaScript is handled. So when it goes from the internal API to JavaScript and then go back to the internal API, how things are working there. And this leads us to talk about the actual vulnerability that we found and to see how we can trigger it. So on the left here, you have the full POC of the POC that allows us to trigger the bug. And we're going to go through the main parts here. So for each promises resolution, we're going to invoke one of the resolution function pair. So here, for example, we call the fulfill function. And until the last element, for the last element, we're not going to call any resolution function, but we're going to store them inside some JavaScript variables. So eventually, we're going to call the call to the promise all settled API will stop. And after that, we're going to call the last fulfilled function that we stored. And it will call the internal API related to it, which at the end of the execution of that API will have a full element store. Here we call the promise all settled function with 12 promises. So here we have 12 result objects inside the element store. And the remaining count will eventually become 0 because all the promises has been resolved. So it will eventually lead to call our custom result function in JavaScript. And inside that function, we're going to trim the values array by using the shift operator until the values array is empty. So when we do that, in the memory, the element store will now be empty, with like the size will be 0. And the last step of to trigger the bug is to call the last reject function, which will call the internal API related to that JavaScript call. And here, we're going to go through the same execution as before. So get the data holder from the JS function and get the index. But here, you can see that the index is 11. So it has not been updated since the values array has been trimmed. So when we continue the execution and eventually get the values array from the data holder and store it, we're going to eventually go to the check if the values array at index 11 is undefined or not. So here we'll actually have an out-of-bound read that will happen. But this out-of-bound read is not very useful because it's just checking if the value at this index is undefined. So what we actually want is to get to the set element function here, which will allow us to write the output object at index 11 inside the element store. So we'll get our out-of-bound write. And if you followed along, it was pretty tedious, but if you followed along, you might have noticed that the out-of-bound write is highly restrictive for a couple of things. First of all, the value that we intend to overwrite must be undefined, because if it's not undefined, we actually won't bypass this check and we won't get the out-of-bound write primitive. And secondly, we lack of control about the object that we're going to write out of bound, because this object is actually created during the internal API execution. So we don't control really what's going on that part. And finally, the values array is located on the nursery heap, and you will learn more about this heap later, but the values array is actually followed by a lot of JS objects in memory. So, and those objects are created during the internal API execution, so it's pretty hard for us, and so they are not controllable because from JavaScript because they are created via the internal API. So it's hard for us to override something that would be controllable from us in JavaScript. So all those issues that we have here, they're going to be answered by Tao during the exploitation part.
Yeah, thanks, Edward. My name is Tao Yan. I'm going to talk about how we exploited this seemingly unexploitable vulnerability. First of all, I will introduce some SpiderMonkey internals, which is required to better understand our exploit. When allocating objects in SpiderMonkey, usually they will be allocated in the nursery heap. When they are not going to use, minor GC is responsible to free them or move them into the tenure heap if they are still in use. And major GC are responsible for the objects in the nursery heap and the tenure heap. Free them when they are not in use and move them into from the nursery heap to the tenure heap if they are still in use. The nursery heap is a linear heap. Objects will be allocated in nursery heap one by one, and so different size objects can be allocated together. In the contrast, objects allocation in the tenure heap are based on the allo kind, which means only same-sized object can be allocated together. Besides object, internal data structures like shapes, base shapes, etc. will be directly allocated in the tenure heap. Triggering major GC, trigger GCs with just JavaScript is very important in the browser exploitation. So we'll introduce how to trigger major GC and a minor GC with just JavaScript. To trigger minor GC, we just allocate large size array buffer. You can see when we allocate the array buffer, it will call the maybe trigger GC after malloc function. In this function, there's a check about the use bytes, which is over 128 megabytes. It's larger than threshold bytes. If it is true, then it will call the request major GC. And in request major GC function, it will finally request interrupt with interrupt reason major GC. The major GC cannot be called directly because some safety issues. So the main thread will find a suitable time to handle the interrupt and trigger the major GC collect. For minor GC, we use a different strategy. We just allocating a lot of JS objects to fill the nursery. Here we just use example. We allocating a lot of JS array, and you can see when we create the array object, the try-alloc cell function will be called, and when the nursery heap is full, this check will be always true because there's no free cell for the new allocated objects. And the retry nursery alloc will be called. Here you can see the runtime minor GC will be finally called. Sometimes, according to some indicators like performance, CPU usage, memory usage, the nursery can be resized. The maximum size is 64 megabytes. So now we have some SpiderMonkey internals. Let's see how we confirm this vulnerability from a highly restrictive out-of-bounds write to the powerful primitives. As we mentioned before, there are some restrictions. To do the out-of-bounds write, we need to allocate a victim object, which should need to be adjacent with a values array element. Then we need to bypass the undefined check, and also the overwritten value cannot be controllable. It is just an address of the object val. So first of all, we need to find a suitable victim object. We just search the undefined value in the SpiderMonkey code repo. Luckily, we find an interesting function named init fix slot in the native object inline header function. Based on that, we can find this call stack, and we found a very interesting object, the class object. And in this object, we can set the properties to undefined. So you can see there's a lot of undefined values in the memory layout of the object C0. So we can control the properties to the undefined. For the size, the object size is based on the fixed number of slot in the shape, and it is calculated by the property count estimate, which is 5 because the property numbers are 5 right now. And the corresponding allo kind of the kind slot 5 is object 8. So we can adjust the property numbers to adjust the size of this object. So it is a perfect object for us to be a victim object, to be overwritten. Then we need to make the values array element and the object we just found to make them adjacent. So let's tracking the values array again and see when the promise static or settle function is called, the promise or settle element function will be called 11 times. At that time, the values array size is 11. And when the last fulfill function is called, the remaining count will be 0, and a call promise result function will call the callback, which is defined in the JavaScript, and the parameter of this callback function is values array we just mentioned before. And then we expose the values array to the JavaScript, and we just shift the element to make the values array to empty, and then we just allocate the victim object C0 as the first element of the values array. Then we trigger the major GC. This is where the magic happens. You can see the move elements will move all the objects in the nursery heap to the tenure heap. And most importantly, the GC will combine the values array and values array element together to inline values array, because the values array size is very small. And right after the allocation of the inline values array, the GC will allocate the object C0 right after the allocation, because according to the deep first algorithm, because the object C0, we can control the size for it, and it shares the same allokind with inline values array, so it can be allocated adjacently. Then we trigger the vulnerability, allocating object val, and finally we bypass undefined check. And when index is 11, the object val address will be overwritten to the property 5 of the object C0. With this corrupted object C0, we still can't exploit, because there's no interesting exploitable scenario. So our idea is transfer this out of bounds right to the use after free. To achieve that goal, we just trigger the minor GC by filling the nursery, and you can see we create a lot of JS array to fill the nursery, and when the nursery is full, and the object array object creation will call the runtime minor GC, and the runtime minor GC will free the junk array and object val. Because the object val reference inside a C0 object is not found by GC, it is overwritten by the out of bounds right, the vulnerability. So all of them will be freed, and then all other JS arrays will be moved to the tenure heap. So right now we have the dangling pointer in the object C0, which pointing to the free space in the nursery heap. It is an exploitable scenario. We can see after the minor GC is called, the next step is we want to reclaim the freed object val object. And then after the minor GC is called, the next array allocation will be allocated in the nursery as the first element. And all other JS arrays will be allocated in the tenure heap, because of this check will be always false. So right now we have the object C0 property 5 pointing to the data section of reclaiming JS array, and we can control the data section of the JS array. So we successfully convert the result free to the type confusion. The next step is to create a fake array to read something interesting based on the type confusion. You can see in the black rectangle, all other fields constant value, which are very easy to be faked, except the fake shape and the inline back install. The inline back install is arbitrary address. Right now we don't have the arbitrary address, but luckily we can trigger the vulnerability again to leak the nursery address by just allocating the big uint64 array right after the inline values array and set the undefined value to the first element of the big uint64 array and trigger the vulnerability. The object val address will be overwritten into the first element of the big uint64 array, and then we can leak the object val address by reading the uint64 array element 0. And do some calculations, we can get the nursery base address. With nursery base address, then you can see we allocate another new array just after the reclaiming array, and we know the address of this new array. It is nursery base plus the A0, so we can fake the inline back install of the fake array to make it pointing to the new allocated array to get the shape. And so our purpose is to read some metadata of this real array. Then we need to calculate how we need to solve the issue of the faking the shape. The shape object is allocated in the tenure heap, and the shapes are the foundations of the type confusion. The easiest way to fake the shape is to make the fake shape pointing to the real shape, but it can't work because we don't know the tenure heap address. So we go deeper to investigate how the SpiderMonkey get the element of the object with int index. Let's see, there's a first check to check the ops property in the JS class, and the JS class is from base shape is from shape. So we can fake everything in the nursery heap just to make the ops property to 0, and we can bypass this check. And there's another check. If the index is 0, it is int. There's a check for the object to see if it contains the dense element. And in that function, it just checks the element value is not just element whole. It is easy to fulfill, and we can also bypass. And so to read the fake array element with int index, we don't really need to fake the whole shape. Just bypass the opportunity check and make sure the element value to be read is not magic element whole. So we can successfully read the element value in the JavaScript. Here is a final nursery heap layout. You can see we can accurately control the array objects allocation and know the address of each object. So in our exploit, we just make things easier, just pointing the fake array, fake shape to the address of uint32 array. Why we do this? You can see the uint32 array shape will be considered to be the fake base shape, and the base shape of the uint32 array will be considered to the fake JS class. And when accessing the faking property, there's an out-of-bounds read, but it doesn't matter because we can do some heap grooming to make sure the memory after the base shape are all 0, and we bypass this check. And the element value is the array shape, which is highlighted by red color, and it is definitely not equal to the element whole. So we can read the JS array shape, the real JS array shape. To be mentioned here, the yellow object can be any object. We just use the array as an example, so we can actually leak any metadata of any object. With that, our purpose is to create more stable fake JS array by updating the real array to the fake array, real shape to the fake shape, and then pointing the backend store of the fake array to the data section of the big uint64 array. Then we can easily have the fake object primitive, because the fake array and the big uint64 array are both pointing to the same memory region. With the fake object primitive, it's very easily to create more powerful exploitation primitives. For example, the address of, we can just write any object to the fake array with the fake array 2, and then read the address of any object by using the big uint64 0. And for arbitrary read, we just updating the inline backing store of big uint64 array to any address, and then we read the data of any address with big uint64 or 0. Similarly, for arbitrary write, we just also updating the inline backing store, and then we can write any value to any address with big uint64 0. Now we have the everything we want. We have address of read-write primitives. Then Edouard will introduce how we can use these powerful primitives to execute the code in the renderer of the Firefox.
I think so. As we really like for code execution, we're going to use the WebAssembly RWX memory. So quick words about some of the internals related to WebAssembly function code in JavaScript. So let's say we create a very simple WebAssembly module that has 2 export functions and returns some simple int32. Let's say we initialize that module and just eventually call one of the WebAssembly function in JavaScript. So here we call F0, and in the underlying JS engine, it will call the following functions here on the right. So in WASM call, what will happen is we're going to access the codis, which is the JS function. And from it, we're going to get access to the WASM instance and store that in a variable. Then we're going to access the function index of the WebAssembly function and use the instance to call the call export function. Inside that call export function, 2 really important things happen. First stuff is to actually get the function pointer, so like the entry points of the code related to the WebAssembly function. And to do that, we're going to do some structure parsing. So from the WebAssembly instance, we're going to get the WASM code. From the WASM code, the WASM compiler tier code block. And from the code block, we're going to get the base address of that. And so the function pointer will be computed based on that base address, plus an offset computed itself on the function index of the WebAssembly function. And eventually, the last internal call here will just jump to the function pointer of that WebAssembly function, which will jump inside the WebAssembly, like the RWX memory created for the WebAssembly module. And it will first jump to a function stub, which will be responsible to call the actual compile code of the WebAssembly function. So with that, the first thing that we want to do after getting arbitrary read writes is to write our shellcode. And in fact, we are not going to use arbitrary read writes to do that. We're going to use a pretty known technique right now is to encode our shellcode into 64-bit floating points. And when we do that, we'll actually, the WASM compiler will compile those values into 64-bit values in the RWX memory. So we'll straightforward have our shellcode written for us, which is a pretty neat technique, I think. And so now that we wrote our shellcode, we just need a control flow hijacking primitive to actually jump to our shellcode. And to do that, as they do for the export function call, we're going to parse some structures. So so using our primitives, we're going to get access to the WASM instance, from the WASM instance to the WASM code, and from the WASM code to the code block. And finally, we'll have access to the base address, and we're going to actually corrupt that base address. So using our arbitrary read write. So when we actually call the function pointer, we'll have corrupted that function pointer, and we can make it point to our shellcode and directly execute the shellcode itself. So to give you like a quick summary of the whole exploit, so we actually trigger the vulnerability once for the and get the out of bound write. Then from the out of bound write, we convert it into use after free. And from the use after free, we are leaking some nursery address, and eventually get the type confusion, and finally get like the classical browser primitives like the fake object, the address of, and finally the arbitrary read write to get the code execution. So we'll do the live demo actually at the very end. So Tao will just give you a quick conclusion.
Okay, to sum up, firstly, it is very worth to take a look at similar implementation issues of cloud in different applications, because developers are prone to make similar mistakes when implementing complex specifications. And so there are a lot of callback issues in the history. And secondly, when you think the bug is not exploitable, maybe you may want to think again and go deep. When you go deeper, you may find something you never thought about before. And for example, we found we can use a unique feature of the SpiderMonkey to fake any object, which is very universal and a stable exploitation technique in the Firefox. And hopefully, you can get some inspirations from our research. Thanks again for your attending, and let's do a live demo right now.
So first of all, we're going to disable the Firefox sandbox because that's a render-only exploit. Let's just double check that it's on, yes. And then let's launch Firefox. And let's take a look at the version here about. And here, so it's 138. Is that the version we pawn at Pantone? Now, let's execute the export server here. And yeah, good. And then let's pray and see if it works first time. Awesome. That didn't work. Let me clear the cache real quick. Like. that's awesome. That's the best demo I did so far. I cannot clear the cache. That's great. Thank you. Let me clear the history real quick. I think that will be the last try since the timing is running up. Yeah, let's close Firefox and run it again. Let's browse. Awesome. Doesn't work. Yeah, okay, last time guys. Oh, yeah. Nice. A bit painful, but we made it, so that's great. Thank you guys for listening to us. That was great. Thank you.